All right. So again, we'll cover 4, 5, and 4, 6. Also, do make sure you're keeping up with your homework stuffs on the My Math Lab. So again, Canvas, I don't push any homework assignments out because it's all in My Math Lab. Make sure you're getting those done. Pay attention to the due dates. All of the chapter 4 stuff, I believe, is due on the 10th, which if I remember right is like the day before we test. So don't plan on working on it the day of. I think it's all due the day before. So make sure you're getting your stuff taken care of so that we don't end up missing out on anything. I need paper. I should probably turn on my screen, huh? All right, 4, 5. Come on. Is all about rational functions. Hold on, I gotta wait for my monitor to power up. If it does, then we'll get going. Hopefully, what I got going on. All right, so again, 4, 5 is all about rational functions, and rational basically just means fraction. You can kind of substitute those for each other. So 4, 5 is all going to be about rational fraction functions. For example, f of x could equal 1 over x. Or something like f of x equals x minus 3 over x squared plus x minus 2. Anyway, you get the idea. You're going to have a fraction, something on top, something on bottom. Just notation stuff. The top is referred to as the numerator. The bottom is referred to as the denominator. Again, that's not something I'm going to ask you, but if in the process of working something out, or if you're trying to get help in My Math Lab, they can use the vocabulary of numerator and denominator, and that's referring to the top or the bottom of the fraction. So if it says something about the numerator, there you go, or denominator, there you go. Something we've already kind of talked about with this is going to get revisited, and that's the idea of the domain of a function. Remember, your domain is all possible x values, or your inputs. It's basically anything your x can be. Your domain is typically all real numbers. However, with rational expressions, the big key we want to worry about is we want to make sure we don't cause division by 0. Okay? Division by 0 is bad. That causes a fraction to be undefined. Okay? If we try dividing by 0, we get an undefined answer. So I guess technically that should be a 0, not an undefined symbol. I wrote the wrong thing. Okay? Anyway, so if you divide by 0, you get an undefined problem. So anything that causes division by 0 needs to be excluded from the domain. So if they ask you specifically what is the domain of some function, okay, your domain is any value that does not cause division by 0. Okay, the numerator is not affected. We just want to make sure the bottom doesn't equal 0. So disregard the numerator. Just take your denominator, your bottom, set it equal to 0, and then solve. If we subtract 2 from both sides, -2 causes this expression to equal 0. So -2 needs to be eliminated from our domain. So again, remember, domain is typically all real numbers. But now in this case, we got to make sure that x does not equal -2. And my math lab in this class, they want us to write that in interval notation. So just like all real numbers was from negative infinity to infinity, interval notation for this, not equaling -2, looks like this, from negative infinity to -2, not included, and then from -2 to positive infinity. These two things here mean the same thing, okay? X cannot be -2 because that causes division by 0. This says what X can be, basically. X can be everything up to -2, and then from -2 on. So really the only number it can't be is -2. It's not included here. So this is the interval notation of this exact same idea. So anytime it asks about the domain, you just have to eliminate any numbers that cause division by 0. Sometimes it's a straight up linear problem. Sometimes they'll give you a quadratic underneath. For example, same type of idea. So what is the domain of, say, x plus 1 over x squared plus 3x minus 10? Again, if we're just talking domain, we're just trying to figure out what numbers to eliminate based off of what would make the bottom equal 0. The numerator is not a limiter. The numerator can basically be whatever the heck you want it to be. It can be positive, it can be negative, it can be a square root, it can be whatever. So it doesn't matter. And the bottom can be anything except for 0. Okay, we can't let the bottom be 0. So our whole goal in this domain is figuring out what causes the bottom to equal 0. Now, also remember that the more stuff that gets involved, the more complicated the problem is. This particular problem is a quadratic. When it comes to solving a quadratic, you really have two choices. We can solve by factoring, or we can use the quadratic formula. I don't care which one you use, they both work. I'll show both. The fact that you have an x squared. So the fact that this is an x squared is what makes this a quadratic. Another thing that kind of helps you out, we talked about this before. Remember that leading degree tells you the number of solutions you should have. So that tells us we're looking for 2 solutions. It's not linear, it's got to be something else. And in this case, it's quadratic. So if your x is squared, you can solve by factoring or the quadratic formula. I'm going to factor this one. Okay, remember we got to figure out what multiplies to get x squared. That's x and x. From there, we're looking specifically for what 2 numbers will multiply to get -10, and we'll also add to get 3x. So what numbers multiply to get -10? That'd be 1 and 10, or 2 and 5. And we need the ones that are going to add to get 3. So that would be +5 and -2. Order doesn't matter, but +5 times -2 is -10. +5 plus -2 is 3. So if we can find 2 values that multiply to get this and add to get this, that's our factors. Then to solve, set your factors equal to 0. So x could equal -5. Or x could equal +2. Basically, both of those values will cause this bottom to be 0, which again is bad. That means that these numbers need to be eliminated from the domain. Now, I know a number of people do not like factoring. They like that quadratic formula. So remember the quadratic formula says x equals -b plus or minus square root of b squared minus 4ac all over 2a. This is just a formula you can use to solve a quadratic. In this case, your a's and b's and c's come from here. This number is your a, number is your b, this number is your c. So then if we just put those numbers into this formula, we get -3 plus or minus square root 3 squared minus 4 times 1 times -10 all over 2 times 1. And then if we use order of operations to simplify this, so that'd be -3 plus or minus, okay, 3 squared is 9. -4 times 1 times -10 is +40. 9 and 40 is 49. That's all over 2. Keep simplifying. Square root of 49 is 7. So we get -3 plus 7 over 2 and -3 minus 7 over 2. -3 plus 7 is 4. 4 divided by 2 is 2. Exact same solution we got there. -3 minus 7 is -10. Divided by 2 is -5. Exact same solution we got there. So 2 different methods that get you to the same place. I don't care which one you use. To me, factoring is a lot more straightforward, but it depends on how good you are at factoring. If you make a mistake and you get the wrong zeros, that's going to screw stuff up. This is one of those things that always works regardless of how the problem sets up, but it's a little more work depending on how you do it. All right. All of that to say, these are my solutions. These are the things that cause bottom to be 0. So these are the numbers we want to eliminate from our domain. So again, the way we say that, and it's got to be in order. So the smallest number comes first and the biggest number we say you can have from -infinity to -5. And then from -5 to +2. And then from 2 to infinity. So again, this is the interval notation. To say we need to eliminate those 2 numbers. So you can have anything all the way up to -5, but not -5. And you can have anything between -5 and 2, but not 2. And then you can have everything from 2 on. But basically, these numbers are the ones that need eliminated. Yes, with interval notation, yeah, in this case. Correct. Yep. So the question was, are the negative infinities and the positive infinities always involved? And the answer there was yes. Because again, our domain is typically all real numbers. This is a typical domain. So we're saying your x can be whatever the heck you want it to be, everything from negative infinity all the way to positive infinity. In this case, when we have to eliminate something, this is kind of the notation for how that would look. So we're eliminating -5 and we're eliminating +2 in between the infinities, if that makes sense. Okay, so as far as rational functions goes, that's anything that would be the domain. The domain, we just have to eliminate anything that would cause division of 0. Now, I'm also going to show you guys something. You remember I'd recommended getting a calculator. Calculators are handy dandy. A calculator will save your life in this case because certain sophisticated calculators will solve this for you. I don't know, it's too dark. I don't know if you'll be able to see it. Anyway, just kind of follow along here and I'll try to show you on my screen. If you have a really nice calculator, and again, this is not an expensive calculator. This is a $15 calculator from Walmart, but this will solve that quadratic for you. So without having to do all of this nonsense or all of this nonsense, okay, on my calculator, I don't know if you can see my screen, hit mode, gives you a host of choices. Come on, there we are. Okay, we want to make sure and solve any equations. So this would be choice 5. I don't know if you can see very well, but we want an x squared. So that would be choice 3. It gives you some zeros. We're going to plug in our A and our B and our C, just like we did for the quadratic formula. So I'm going to plug into the calculator 1, and then 3, and then -10. And if I just hit the equals button, okay, it'll generate my solutions for me. It says x equals 2, and then it says x equals -5. So if you have the right calculator, you can do all of this on your calculator. Now, same thing, if you couldn't really follow this, if it was too dark for you to see, very easy, just Google. Okay, finding zeros. Using whatever the heck calculator you have. So it'll have some model number somewhere. In this case, this is the Casio FX 115 ES Plus. If you just Google that, it'll almost always generate like a YouTube video or some kind of walkthrough of how to solve using your calculator. If it doesn't exist, then your calculator can't do it. Not every calculator can. But nowadays, especially a newer calculator, they're very sophisticated and they can do a bunch of nifty things. So that's just a heads up and a benefit of having a fairly sophisticated, decent calculator. And again, that does not mean go buy a $1,000 calculator, a $200 calculator. If you've got a cheapo $15 calculator, they can still do it. This, like I said, this particular calculator, I think it costs $15 at Walmart. So anyway, it'll save you some headaches, I promise. All right, wow, that was a lot of talking for just the initial part of this. So domain, you're just seeing what to eliminate because it causes division by 0. Another thing to deal with rational functions. Okay, we're kind of talking graphing these functions. And on my math lab, it's going to ask you to match the graph. You're not going to have to specifically graph, but you are going to need to match. So there's a couple of things they could ask you. So a word that I've talked about a couple of times, and I don't remember if I've defined it or not, but an asymptote is an invisible line that a graph will approach but not cross. And rational functions could potentially have vertical asymptotes. They could potentially have horizontal asymptotes. Or they could potentially have what we call an oblique asymptote. First, I want to go to a graph where I can punch this in and kind of show you what I'm talking about. And then I'll show you how to find these. So if I share my screen, we'll see if this will play nice. Actually, I should probably pull this up first. Right, hold on, give me 1 second. Obviously, us here, we can see the graph. Waynesville Republic, can you guys see my graph?
Yep.
Yes?
Yes.
Awesome, great. All right, so again, in Desmos, I love Desmos. It can graph everything for you. I'm going to take that same function I just had, and I'm going to sketch it in here. All right. So you see that kind of this funky graph. Okay, we got curves all over the place. Okay, you can't really see it, but if I draw this in here, oops. okay? If I draw that blue line here at y equals 0, you can see we have a horizontal line. And this graph actually, depending on how zoomed in you get, you won't ever cross that line. You keep getting closer and closer and closer to it, but you'll never cross it, really, in both directions, okay? So this is what we call a horizontal asymptote. And then it looks like there, I drew this line in here. This is an example of a vertical asymptote. This green line, if you can see it, I don't know how zoomed in you guys are, but that's a green vertical line. Again, if you zoom, this graph will keep getting closer and closer and closer to that green line, but it's never going to actually get there, and it's never going to actually cross that line. Okay? So that's the idea of an asymptote. These graphs are approaching these lines, but they never actually cross them. So next, I'm going to show you how to find those asymptotes. And that's some of the things they're going to ask you in my math lab. It's like, where are the vertical asymptotes or where are the horizontal asymptotes? Okay. Vertical asymptotes occur when the denominator equals 0. So those exact same numbers we were eliminating in the domain is where your vertical asymptotes occur. So whatever causes the bottom to be 0 is going to give you a vertical asymptote. So this is basically the exact same thing that we did when talking about the domain. Okay, those numbers that we were going to eliminate because they were bad makes sense now because your graph will never cross those values. There is no value at those points because it's undefined. That's why there's an asymptote. You can't get there. It's undefined. Okay, so this particular function here, so this 2x minus 11 over x squared plus 2x minus 8. I'm going to show you how we would find or where we would find our vertical asymptotes. So okay, again, focus on the denominator. We're going to figure out what are my zeros. What causes this to equal 0? So we don't worry about the top. We just look at the bottom. What makes my bottom equal 0? And again, you can solve this using your calculator. You can solve this using the quadratic formula. I'm going to factor. So again, specifically, I'm looking for two numbers. I need to know what two numbers multiply to get -8, but also add to get +2. So again, numbers that multiply to get -8 are 1 and -8, 2 and -4, or 4 and -2. Okay, and we got to figure out which ones are going to add to get +2. So that's going to be +4 and -2. 4 times -2 is -8. 4 plus -2 is 2. So these are my factors. So if we set those equal to 0 and to solve, we get 2 and -4. And this is literally the equations we would use for those vertical asymptotes. So you have vertical asymptotes at x equals -4 and at x equals 2. And if I go back to this original graph, I typed in x equals -4. That gave me this vertical asymptote. If I type in x equals 2, This purple line represents my other vertical asymptote. So using that exact same function we just solved, we solved for this piece and for this piece, and that's where my vertical asymptotes are. That's my vertical lines that these graphs will never cross. I could zoom out. Okay, you can see a better idea of what this curve kind of looks like. Okay, and these curves won't ever touch those lines. So that's where my vertical asymptotes are. So again, your vertical asymptotes are anywhere that causes your denominator to be zero. It's pretty much just like what we did for domain, but we don't need that interval notation anymore. These are where my vertical asymptotes occur. Yep, anything that sets your denominator equal to zero. Yep.
That's the action.
Yeah, yes. Yeah, so the question was why we went from the x plus 4 down to the, whoops, get where I can see this, why we went from x plus 4 to the negative 4. So if, again, this is going back to a previous lesson, these are my factors at x plus 4 and x minus 2, and these are my zeros. So these are the actual numbers that cause this to be 0. So if I plug negative 4 in, negative 4 plus 4 is 0. That's what causes this to be 0. So just for clarification. Okay, so again, it'd be the exact same. So if I, without drawing another problem, if we went back and revisited this one initially, so this x plus 1 over x squared plus 3x minus 10, okay, we solved x equals negative 5 and x equals positive 2. This is where my vertical asymptotes would be. So I would have vertical asymptotes at negative 5 and positive 2. So just like we eliminated for the domain, okay, that's where my vertical asymptotes would be. So again, if we go back to this original problem, 1 over x plus 2, I would have a vertical asymptote at negative 2. So the same numbers you would eliminate from the domain are the same exact places where your vertical asymptotes occur. So same idea. All right, horizontal and oblique. Okay, if the rational expression has a horizontal or an oblique asymptote, it will not have both. It will either be one or the other. So you will not have both a horizontal and an oblique asymptote. That's not possible. So you will either have horizontal or you will have oblique, but not both. And that's based off of the degree of your numerator and the degree of your denominator. Okay, so 3 different problems. If the degree, okay, the exponents, that's kind of what we're talking about. So looking at the biggest exponent. If the exponent is bigger on the denominator than it is on the numerator, so something like this, 1 over x squared, or even say x plus 1 over x squared. If the exponent is bigger on the denominator, your horizontal asymptote, I'm going to abbreviate that so I don't have to keep writing it out. Your horizontal asymptote is at 0. Y equals 0. That'd be a horizontal line on the y or on the x-axis. Correct. If the degree of the denominator is bigger, so I can put any number I want to in front. So if I said 5x plus 1, we're just looking at the exponents. If the exponent on the denominator is bigger, then your horizontal asymptote is at 0. Specifically, y equals 0. If the degrees are the same, so these are both x squareds, if these would both be x cubes or even x to the fifths, whatever, okay, if your biggest exponents are the same, then you also have a horizontal asymptote, and it's going to be at the ratio of coefficients. So again, the number in front of x squared, if you don't see it, it's automatically a 1. So we grab the numbers in front. So your horizontal asymptote would occur at 1/3. Okay, I'm going to do 2 more examples of those exact same problems because this one would have an oblique asymptote. I'll talk about that one in just a second, but I want to make sure we got a good idea or a good handle on the horizontal asymptote. So I'm going to pick 2 different problems. So if I had 3x squared plus 2x plus 4 over x to the 4th minus 1, as long as your degree is bigger on the bottom, again, this one's going to have a horizontal asymptote at y equals 0. Can't read my crappy handwriting that says 5x to the 4th plus 3x squared over 4x to the 4th minus 2x squared. If your degrees are the same, you also have a horizontal asymptote, and it happens at the ratio of those coefficients. So again, the x to the 4ths are my biggest exponents. Since they're the same, I just grab the numbers in front. In this case, that would be 5 and 4. That's where my horizontal asymptote occurs. All right, if the degree on top is bigger, in this case, I pick x cubed plus 1. That's probably not a great problem. I'm going to change my problem up a little bit. But if the degree on top is bigger, you're going to get an oblique exponent. Oblique just means on a diagonal, okay? Vertical is up and down, okay? My goodness. Horizontal means left and right. Oblique is basically any other angle, okay? Not straight up and down, not straight horizontal, not straight left and right. If it's on some kind of angle, like so. On focus, you can do it. Okay, so again, vertical, straight up and down, horizontal, straight left and right. Oblique is just some kind of angled line. All right, to find an oblique asymptote, I'm going to change this to an x squared plus 1 so it plays a little nicer. Okay, we're going to take the idea of division. So we've basically got to take that x squared plus 1. You take the top divided by the bottom. And the easiest way to do this is that synthetic division that we did a couple lessons ago. So again, we're going to grab the opposite. So x plus 1 means we're going to grab a -1. And then I'm going to grab the coefficients of this guy. So I've got 1 x to the 2nd. I'm missing my x term, so I need to put a 0. And then my constant is 1. Then we follow that pattern, add, multiply, add, multiply, add. So I get x, there's my constant, so x minus 1 with a remainder of 2. This x minus 1 is where my oblique asymptote would be. So that equation, so y equals x minus 1, will give me a diagonal asymptote. because I was missing an X term, there was no X term here, so then I needed 0 as a placeholder. Now, all of that to say, there will only be, I believe, one problem asking you about an oblique asymptote in your homework, and I will not put that on the test. We're doing synthetic division with other stuff, so I'm not going to spend a lot of time on this one, because if you specifically needed to graph a problem like this, you would use Desmos, just like I would use Desmos. I'm not going to hand sketch this thing, okay? Horizontal asymptotes is stuff that will show up. Oblique, I will not put on the test in this particular case. And I think there's only one homework problem involving that. But you should be able to find your horizontal asymptotes. Again, if the degree on bottom is bigger, the horizontal asymptote is at 0. If the degrees are the same, it's that ratio of coefficients. Basically, just grab the numbers in front. Now, also remember your vertical asymptotes where X equals. Your horizontal asymptotes are Y equals, so pay attention to that. Same with the oblique. Your oblique one is also a Y equals, but it's not a pretty little whole number. It's going to be some equation. All right, so if they gave us a problem like this, come on, focus. Okay. If f of x equals 3x over x squared minus 6, and they told us to find all asymptotes. Okay, the first thing I'm going to look for is I want to look to see if there are any vertical asymptotes. So again, I'm going to take my bottom, my denominator, that x squared minus 16, and I'm going to find out what values, if any, make that equal 0. Again, this is a quadratic, so we can solve using our calculator. We can solve using the quadratic formula. I'm going to factor again. So x squared is still x times x. Then I'm looking for two numbers that multiply to get negative 16 and then add to get, my middle term is gone, so I need them to add to get 0. So that's going to be positive 4 and negative 4. 4 times negative 4 is negative 16. 4 plus negative 4 is 0, represents the middle term that's gone. So then I set those equal to 0. Negative 4 causes that to be 0. Positive 4 causes that to be 0. This is where my vertical asymptotes would be. So I've got vertical asymptotes at x equals negative 4 and at x equals positive 4. They could. If they asked for the domain, then you would have to worry about the domain. In this particular case, they just asked about asymptotes. So in this case, we're not worried about the domain, but it's basically the same thing. Like if you found those two values, if for some reason they ask you for the domain of this function, domain, okay, it would be from negative infinity to negative 4, from negative 4 to 4, and then from 4 to infinity. So again, same idea, just different question. Again, they were saying find all asymptotes. These are my two vertical asymptotes. Horizontal or oblique. Remember, that depends on your degrees. Looking at just your exponents, where is the bigger exponent? In this case, the bigger exponent is clearly on the bottom. If the bigger exponent is on the bottom, then you have a horizontal asymptote at y equals 0. And that's a typical question in my math lab. It's going to give you some sort of rational function, and it's going to say something to the effect of, hey, find all of the asymptotes. And then it's going to give you a place to list them. Remember, verticals are always in terms of x equals, horizontals and obliques are always in terms of y equals. All right, the last thing, because we're talking about graphing functions, they may ask about x-intercepts and y-intercepts. Your x-intercept is where the graph crosses the x-axis basically that's whenever y is 0. Your y-intercepts are where the graph crosses the y-axis, or basically whenever your x is 0. Okay, so if they gave us a function, okay, x plus 3 over x squared minus 9. And if they asked us what is your x-intercept? Okay, it's basically whatever causes our graph to be 0, or where the graph crosses the x-axis. Okay. Now, this is easier to see from the graph, but we'll also point this out. Okay, we're trying to figure out what values cause this to equal 0. In this case, there aren't going to be any. If we set this up equal to 0, and we go to solve, we would get -3. However, that causes this to be undefined, so there is no value at x equals -3. So there is no x-intercept in this particular problem, which also makes sense because if we look at this problem, since our degree on the bottom is bigger, my horizontal asymptote is on the x-axis at y equals 0. So if my horizontal asymptote is on the x-axis, I'm never going to cross it. If I never cross the x-axis, I never have an x-intercept. So if your horizontal asymptote is on y equals 0, you have no x-intercept. Good news is the y-intercept is easy to find because then we just plug 0 in for x. So what is my y-intercept or intercepts? You put 0 in for x. So we put 0 in here for x, 0 plus 3. We put 0 in here for x, 0 squared minus 9. 0 plus 3 is 3. 0 squared is 0. 0 minus 9 is -9. 3 over 9 reduces to 1/3. So my y-intercept is at negative 1/3. So that would be the point 0, negative 1/3. That just means where you're going to cross the y-axis. So again, I'm going to jump to Desmos. I'm going to show that graph so that we can talk about it. So if I share my screen, okay, get in here to Desmos. We got x plus 3. Squared minus 9. These things. Right now. Okay. Again, x and y intercepts. This is my x axis, the horizontal axis here. You can see you never really cross it. It looks like you get really close, but if you zoom this thing in, you can always see there's a gap. Okay, and it doesn't matter how far you go down or how big this gets, you get really close, but if you zoom in, you can see there's always a gap. You never actually get to or touch the x-axis. If you zoom out, it looks like you do, but if you zoom in, you can always see there's a little bit of a gap there. So that's why we never cross the x-axis. And then y-intercept is where we cross the y-axis. So if I zoom this in, say right here, at 0 and then negative 0.3 repeating, so that's negative 1/3. That's where my y-intercept is. And that's what we found here, okay? We had no x-intercept because we had that horizontal asymptote at 0, and our y-intercept was 0, negative 1/3. So if it specifically asks you about x and y intercepts, your x-intercept is what causes the whole function to equal 0, if it exists. And then your y-intercept, you just plug 0 in for x. Do another example of that. Okay, so we're going to do 3x squared minus 11x minus 4 over x minus 4. And we want to find our x and our y intercepts. Again, our x-intercepts are whatever causes this whole function to equal 0. And now we do have to worry about it because if our bigger degree is on top, okay, then we have an oblique asymptote. That just means our graph is going to be on a curve. So we probably are going to cross that x-axis. So we're going to solve this if we multiply everything by x minus 4. Get rid of that. So then again, we're left with 3x squared minus 11x minus 4 equals 0. So we've got to figure out what values work for this. Now, when you have a number in front of your x squared, this is harder to factor. So I'm going to walk through the quadratic formula again. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. If you can't read those, so b was negative 11, so there's 11. That's negative 11 squared. Minus 4 times a was 3. C was negative 4. And then 2 times a, which is 3. So again, this comes from the quadratic formula. And if we just work this out, I'll write a little bigger so we can see it. So 11 plus or minus square root of negative 11 squared is 121 negative 4 times 3 times negative 4, positive 48. That's a little over 2 times 3, which is 6. I'm just using the quadratic formula. I'm walking through step by step how to solve. So we get 11 plus or minus 121 plus 148 is 169. Square root of 169 is 13. Okay, so you breaking up the plus or minus. Again, the square root of 169 is 13, so we get 11 plus 13 over 6, and then 11 minus 13 over 6. So 11 plus 13 is 24. 24 divided by 6 is 4. 11 minus 13 is negative 2. Negative 2 divided by 6 is a negative 1/3. So I should have x-intercepts at 4 and negative 1/3. But if I go back and look at my original problem, what's wrong with 4? 4 is going to cause this to be divided by 0, which is undefined, so you can't have an x-intercept of 4. So that's no good. So in this case, your only intercept is that x equals negative 1/3, or the coordinate negative 1/3, 0. So again, what causes this to equal 0 is now when the top is 0, which is what we solved. But if we go back and check our solutions, my positive 4 actually causes division by 0, so we have to eliminate it. It can't be an intercept. So this is the only one that can. And again, writing your x-intercept as a coordinate is always your x value and then comma 0. That's where you're going to cross your x axis. So again, if we're looking at the graph, at negative 1/3, 0 is where I'm going to cross my x-axis. So whatever the graph does, it's going to cross the x-axis here. Okay, the y-intercepts are actually easier to find. You're just going to plug 0 in for all of your x's. So we'll do 3 times 0 squared minus 11 times 0 minus 4 all over 0 minus 4. So again, to find the y-intercept, all I got to do is plug 0 in for my x's. 3 times 0 squared is 0. Negative 11 times 0 is 0. 0 minus 4 is negative 4. 0 minus 4 is also negative 4. Negative 4 over negative 4 is 1. So my y-intercept is going to be at the point 0, 1. So again, x-intercept's harder to find. It's what makes your function equal 0. Work it out. See if any of your values are undefined. Y-intercept's much easier. Just plug 0 in for your x's. Use math to work it out. 0 minus 0 minus 4 is negative 4. 0 minus 4 is negative 4. Negative 4 divided by negative 4 is positive 1. So your y-intercept is at 1. So that's all of the things they're going to ask you to do. They might ask you to match the graph, but basically all of this information will make sense. Again, your x-intercept is where your x-axis will cross. Your y-intercept, okay, is where your where your graph is going to cross the y-axis. Asymptotes are your vertical lines or your horizontal lines that you're not going to cross. And if you're ever curious about how it matches up on the graph, use Desmos. Desmos graphs everything. Okay, so you can use that. Double check. All right, last section for this unit, 4.6. 4.6, come on, focus. Come on, there we go, okay. 4.6 covers polynomial inequalities and rational inequalities. Okay, polynomial inequalities and rational inequalities. It's two kind of different topics. They solve very similarly. All right. Since we've been talking about the rational functions, I'm going to talk about the rational ones first. So if we needed to solve x minus 5 over x minus 3 is greater than or equal to 0. So again, an inequality just means it is not equal to. So we're talking greater than, equal to, or like less than or equal to. So less than or greater than, less than equal to, or greater than or equal to. These are your inequalities. So that's what we're talking about. Everything before was always equal to something. These are going to be either greater than or less than. Okay, the way we solve these is we are looking for what we're going to call critical points. Okay, and basically your critical points are whatever causes either or the numerator or the denominator to equal 0. So again, if the denominator equals 0, you've got some undefined function. And then when your numerator equals 0, that's what causes this to be 0. So our critical points occur when either the numerator equals 0 or when the denominator equals 0. So if we solve this, add 5 to both sides. Okay, x equals 5 is a critical point. We solve this, add 3. X equals 3 is a critical point. Now, to talk about the solution, this is a little crazy. Just kind of pay attention or kind of follow me along. This will get better as we do some more examples of this, but we're looking at a number line. So if you remember how number lines work, so essentially, well, we'll just do it this way. So if this is 0, 1, 2, 3, 4, okay, 5, 6, number lines get bigger as you go along. They get smaller as you go to the left. Okay. So if we're talking about a number line, these are two critical points on the number line. So at 3, we're going to have a critical point. And at 5, we're going to have a critical point. What we want to know is what happens on either side or in between those critical points. So we're going to choose something over here and we're going to test it. We're going to choose some point in between and we're going to test it. And then we're going to choose some point over here and we're going to test it. Okay. All we're looking for is positive or negative because we want to see how this relates to 0. Okay. So again, just kind of follow me. We're going to pick some point over here. It does not matter which point we pick. We could pick negative 100 or negative 4 or negative 1. I'm going to pick 0 because zeros are easy. And I'm going to plug it into my function. So if I plug it in, I do 0 minus 5 divided by 0 minus 3. Okay, if I work this out, 0 minus 5 is negative 5, 0 minus 3 is negative 3. Divide, I get positive 5/3. So I get a positive value. That's all I'm worried about, positive or negative. Hopefully that'll make sense here in just a second. Okay, I'm going to do the same thing. I got to choose a point in between. So I'm going to choose 4. I could choose like 3.1, or I could choose 4.99999, but I'm going to pick 4 because it's a whole number. All right. Again, I'm going to plug it in. So 4 minus 5 over 4 minus 3. 4 minus 5 is -1. 4 minus 3 is 1. -1 divided by 1 is -1. That's a negative number. Again, I can choose a point over here. I can choose 6 or 7 or 8 or 9 or 10 or a billion. It doesn't matter what number I pick. I'm going to pick 8 just because it's far enough over here out of the way that I can write it down kind of like I did. So I'm going to do 8 minus 5 over 8 minus 3. 8 minus 5 is 3. 8 minus 3 is 5. So I get a positive 3/5. So again, that's going to be a positive value. All right. So what that represents is, since these are my critical points, this is kind of like my breaking points. Okay. Everything smaller than 3, if I plug it in, should generate a positive answer. I picked 0, but it wouldn't matter if I picked -3 or -4. If I pick some value over here and plug it in, I'm going to generate a positive solution. Any number I pick in between is going to generate a negative solution. And any number bigger than 5 is going to generate a positive solution, which again, that's what we're looking for because we want to know how this problem relates to 0. Remember, positive numbers are bigger than 0. Negative numbers are not. So if I'm trying to figure out what makes this greater than or equal to 0, it would be anything that would generate a positive solution. So all of these numbers will generate a positive solution and would therefore be bigger than 0. Similarly, all of these numbers, okay, also generate a positive solution and therefore will be bigger than 0, whereas anything in between does not. So again, this is what a graphic solution looks like. We're going to write this in interval notation. So we would say from -infinity, that's this negative forever, all the way to 3. And we would also go from 5 to positive infinity. So this is my interval notation for my solution. So this is just an interval way to say exactly what this is saying. So we use our number line to check our solution or whatever, and then this is how we would write it using interval notation. Now, also remember the brackets here came from the fact that we used closed dots, which came from the fact that this was a greater than or equal to. Remember, greater than, equal to, less than, equal to is where we're going to use our brackets. Just regular less than or greater than is where we would use parentheses. Okay, so we use brackets because this was a greater than or equal to, that line there. Okay, we'll do a couple more examples. Okay, say we've got 2x plus 1 over x minus 3 is less than 0. Again, we're looking for those critical points. Okay, basically in this case, again, the critical points are what causes my numerator and my denominator to equal 0. So 2x plus 1 equals 0, or x minus 3 equals 0. This is going to define those critical points. So if we solve, subtract 1 from both sides, 2x equals -1. Divide by 2. X equals -1/2. 3 to both sides. X equals 3. So again, this generates my critical points. So on a number line, remember the smaller numbers go to the left. Your bigger numbers go to the right. So make sure whenever we put this on our number line, it doesn't really matter where we put -1/2 or 3. Just understand that the bigger number has to be somewhere over here to the right. Your smaller number has to be somewhere over here to the left. And it would go in line. If we had more numbers, okay, make sure they go in order from small to big. Okay, then again, we're going to choose some point in between. Doesn't matter which. And we're just going to test those by plugging them into our original problem. So if we wanted to pick something smaller than -1/2, that could be any number of things. Could be -2, -4, -100. Okay, I'm going to pick -1. That would be smaller than -1 here. It'd be over here. So I'm just going to plug that in. So if I plug -1 in, 2 times -1 is -2. -2 plus 1 is -1. -1 minus 3 is -4. -1 divided by -4 is a positive 1/4. So again, this is going to generate a positive solution. So everything in this region is going to generate a positive solution. Okay, if I pick something in between -1/2 and 3, really easy between a negative and a positive, I'm going to choose 0. It wouldn't matter. I could have picked 1 or 2, okay? But I'm going to pick 0 because zeros are nice because they just go away. 2 times 0 is 0. 0 plus 1 is 1. 0 minus 3 is -3. So that generates a negative solution. If I pick something over here bigger than 3, like 4 or 5 or 6 or 7, okay, I'm going to pick 4. So 2 times 4 plus 1 over 4 minus 3. 2 times 4 is 8, plus 1 is 9. 4 minus 3 is 1. 9 over 1 is going to generate a positive solution. Okay, so again, everything outside is generating positives. Everything inside is generating a negative. Now, pay attention to what we're looking for. In this case, it was just a regular less than, so I used open dots. Also, on interval notation, we're going to be using parentheses, not brackets, just so you know that. Now, in terms of this case, we wanted numbers less than 0. So what kind of numbers are less than 0, negative or positive? Okay, should be the negative one. So in this case, the negative solutions are going to be my good solutions. Okay, everything that's going to be less than 0 is anything that generates a negative solution. Anything that generates a positive solution will be bigger than 0. So these are no good. So our only good solutions are everything in between here. So again, the way we say that with interval notation is everything between -1/2 and 3. We're trying to figure out what solutions, what can I plug in for X that make this a true statement or make this work. Okay, and what we showed on the graph is if I plug in anything bigger than 3, I'm going to get a positive number here, and a positive number is not smaller than 0. So again, this is saying this has to be smaller than 0. So for this to be smaller than 0, it has to be negative. And the only numbers that generate a negative solution are between here. All your positive solutions generate something bigger than 0, so that's no good. So in this case, we wanted the negative solution. If we go back to the previous problem, okay, we were looking for stuff that's greater than 0, so we were looking for the positive solution. So in this case, the numbers that generated positives were good. with this problem being a less than, the negative solutions were the good.
When you put 4 in, how'd you get a positive 1?
Because 4 minus 3 is 1. So again, I plugged 4 into my original problem. So 2 times 4 plus 1 was 9. 4 minus 3 is 1. So 9 divided by 1 is going to be positive. Okay, the only other tricky thing they can do with this, dirty dogs, is they'll change your number on you. Okay, if they do this, okay, we got to get the 3 on the other side. We got to get it in terms of 0, okay, because we want to know positive or negative. That's how we solve all this. So we've got to subtract the 3 to get it over here onto the other side. But now that changes our critical points. Okay, the x plus 2 is still going to be one of those critical points because it causes division by 0. So that won't ever change. Your denominator being 0 is always bad. So that's always going to generate one of those critical points. But now the top being 0 doesn't necessarily matter because of this minus 3. So we have to solve for whatever would make this whole thing equal 0. And that'll be my other critical point. The way we do that, we got to get rid of the x plus 2 on the bottom. So we've basically got to take x plus 2 times everything. It has to be, x plus 2 has to be a critical point. Anything that causes division by 0 is going to be one of those critical points. But we also got to figure out what makes this whole thing equal 0 to find my other critical point. So like I said, I'm going to take x plus 2 times everything. And when I do that, my x plus 2's cancel out there, leaving me with just x plus 1. Because multiplying and dividing by the same thing, they cancel. Then we get x plus 2 times negative 3. And then we get x plus 2 times 0. Work this out. Distribute. Okay, we distribute that negative 3. Negative 3 times x is that negative 3x. Negative 3 times 2 is that negative 6. And then 0 times anything is 0. Combine like terms, 1x minus 3x is negative 2x. And 1 minus 6 is negative 5. So basically, this is going to generate that other critical point. I'm going to write it up here. We could obviously keep solving, okay, but I want to do it kind of in conjunction with that. So once we get to there, that's where my critical points are going to occur. So again, all of that worked to here. When we solve this for x, that's going to generate that other critical point. So again, the denominator cannot equal 0. So that x plus 2 equals 0 is always going to be one of those critical points. So if we solve, we're going to get negative 2. And then again, the idea of whatever makes this whole thing equal 0 is going to be my other critical point, and that's where this stuff came from. We were figuring out what made this equal 0. So I distributed my x plus 2, combine like terms, and then I'm just going to solve. So add 5 to both sides, divide by negative 2, and we get an x is a negative 5 halves. And just to compare, because some people don't know how this fits on a number line, remember negative 5 halves could also be written as negative 2.5. My math lab is going to want a fraction. I don't care if you do a decimal, but my math lab is going to want the fraction. Anyway, so same deal here. With negative numbers, negative 2.5 is smaller. So it's going to fall to this side. Negative 2 is bigger. So it's going to go here. And again, we've got to test some stuff. Okay, again, greater than or less than, no equal to. This is going to be open dots. Again, we'll use parentheses on our interval notation. Okay, now, for me, I'm going to plug it into this function because then I can look at positive or negative, which is what I want to do. You can do it here and relate it to the 3, but it's going to make more sense if I plug it into this one where I move the 3 over. So if I pick a number smaller than negative 2.5, doesn't matter what I pick. I can pick negative 3, negative 4, negative 5, negative 6. Okay, it doesn't matter. Just pick a small number, something smaller than negative 2.5. I'm going to pick negative 4. Okay, and I'm just plugging it into here. So I'm plugging it in all of my x's. So negative 4 plus 1 is negative 3. Negative 4 plus 2 is negative 2. Negative divided by negative is a positive, so that's 3 halves or 1.5. Minus 3 is negative 1.5. So this is going to generate a negative solution. Okay, and just like before, it's going to alternate. So without having to show you that you tested here and here, which you could test, just prove them right, but it's going to alternate. So guess what? This, assuming you did these numbers correctly, that's a negative, then that one's going to be positive, that one's going to be negative. So notice from the previous 2 examples, they alternated. It went plus, minus, plus, and the other one went plus, minus, plus. This one goes minus, plus, minus. They're always going to alternate. So anyway, just to prove it, if I plugged in a point in between, I don't want to pick that because that's going to be a decimal. So between negative 2 and negative 2.5, if you wanted to check, you can plug in negative 2.25. We want to pick something bigger than negative 2. Okay, I'm going to choose 1. So then I could do 1 plus 1 over 1 plus 2 and minus 3. 1 plus 1 is 2. 1 plus 2 is 3. 2/3 minus 3 is going to be a negative 2 and 1/3. So again, it's going to generate a negative solution. Anyway, it's going to alternate. So now relate that back to the original problem. In relation to 0, the numbers greater than 0 are the positive ones. So that's the solutions we want. So again, the positive numbers are the ones that are going to be greater than 0. So those are my good solutions. So my solutions are everything between negative 2.5 and negative 2. And again, greater than is why I use the open dots. That's why I'm using parentheses here. Now also, again, my math lab doesn't like the negative 2.5, so it's going to negative 1, negative 5 halves, 2. I forgot about that. It's going to say write your answer as an integer, as a simplified fraction, not as a decimal. So even though this is correct, my math lab would yell at me. Oh, yep, you're right. Yeah, that was still negative 2, like I had written down clearly. Had that the whole time. Yep. I just wanted to prove that it's really easy to drop a negative sign, just like everybody does. Anyway, all right, so that's your rational functions, or rational inequalities, sorry. Okay, polynomial inequalities play similarly, but in my mind, they're actually kind of easier to find those critical points. So a polynomial inequality we're basically gonna do the same thing, We're looking for critical points. Your critical points are those zeros. So if you're finding a pattern of what we're going to do, guess what? We're going to find zeros. So again, you can factor, you can use your quadratic formula, which again, all of this factoring stuff is why I wanted to show you that finding it on the calculator is so much faster and more accurate than doing it any other way. So if you have a calculator that will solve this for you, holy moly, use it. Okay. No, you can do cubes or linear. Yep. And I'll walk you through because we actually do a cubic one. So I'll show you how to do it on your calculator as well. Yep. Yeah. So depending on the calculator, some calculators are more sophisticated and can do more things. The more sophisticated your calculator is, the more it can do for you without you having to do any of it on your own, which is really kind of handy dandy. And if you have questions about that, I don't want to spend the whole time in class talking about it, but if you'll just email me or text me or whatever, a picture of your calculator, and I can tell you what kind of problems and how to walk through it. Or again, if you just straight up Google it. If you Google it, calculator model number, finding zeros, it'll walk you through step by step how to do it. Okay. So anyway, x squared plus 5x minus 14. You can solve using your calculator. I'm going to factor. Okay, x squared is x times x. So I'm looking for what's going to multiply to get negative 14 and also add to get 5. In this case, that would be positive 7 and negative 2. So again, what makes those equal 0? So set those equal to 0 and solve. So given my original problem, okay, my critical points are those zeros. What causes the polynomial to equal 0? Those are going to be those critical points. So in this case, we've got negative 7 and 2. Otherwise, this plays the same as the rational ones. On a number line, smaller numbers go to the left, bigger numbers go to the right. So we need negative 7 to the left, positive 2 to the right. Also, same, this is just regular greater than, not equal to. So it's open dots. We're going to use parentheses whenever we do our interval notation. And same, we're going to test these areas. And all we're looking for is positive or negative. To do so, again, we just plug it into our original function. So if I pick a number bigger than 2, like 3, plug it in. Okay, so 3 squared plus 5 times 3 minus 14. 3 squared is 9. 5 times 3 is 15. So 9 plus 15 is 24. 24 minus 14 is 10. The actual number doesn't matter. I just need to know that it's positive. Okay, again, if I pick a number in between, anything between positive 2 and negative 7 would work, like 1 or 0 or negative 5 or negative 6. Okay, I'm going to plug in 0. Zero squared is 0. 5 times 0 is 0. 0 minus 14 is negative 14. So again, that's going to generate a negative solution. And if I pick a number smaller than negative 7, like negative, so I'm going to pick negative 10. So negative 10 squared plus 5 times negative 10 minus 14. Negative 10 squared is positive 100. 5 times negative 10 is negative 50. 100 minus 50 is 50. 50 minus 14 is 36, I think. Doesn't matter. It's still going to be positive, which is all that matters.
So it's the zero line that, or it's
You got to set it equal to 0. So if there is stuff over here, you're going to subtract it over because it's got to be in relation to 0. That's so the positive negative thing makes sense. So you always want to set it equal to 0.
because on the last one,
We had to move it over. Yep. Okay, so we'll do the same thing. And I'll show you one whenever we have to move it over, whatever. Anyway, so again, we're looking for good solutions. We're looking for anything that would be bigger than 0. The numbers bigger than 0 are the positive ones. So in this case, the positive solutions are my good solutions. Anything negative would be less than 0 and therefore bad. No good. Okay, so my good solutions are anything that would be positive, which is all of these here. So interval notation again says from negative infinity to -7, and then from 2 to infinity. And again, we use parentheses here because this was a regular greater than, not a greater than or equal to, or not a less than or equal to. So there's the interval notation for my solution. Okay, similar example, but now we're going to actually have a value on the other side. And the question was brought up just before, we need this to equal 0, just like before, and that's exactly true. So if they give you crap over here on this side, we got to get rid of it. We got to move it over here. So we got to move this x over. I'm going to write it underneath this one because you can only combine like terms. So in this case, 3x minus x is going to be 2x. Okay, same thing. We got to get rid of this -8. So to get rid of my -8, I'm going to add 8. And again, I'm going to write it underneath the one that I can combine it with. I can't combine 8 with x squared. I can't combine 8 with x. I can only combine constants. So that's why I lined those up. Anyway, -8 plus 8 is 0. -16 plus 8 is -8. So again, it has to be in reference to 0. For the method we're using to solve, for that to work, it has to be in reference to 0. So if they give you crap on the other side, get rid of it by adding the opposite. Okay, the opposite of positive x was a -x. The opposite of a -8 was a positive 8. And again, you can only combine like terms. That's why I lined it up with the stuff I could combine it with. Anyway, at this point, we go back to doing pretty much the exact same thing. We've got to find those critical points. Those critical points occur when we get 0. So we can solve using the quadratic formula or factoring. Again, for me, factoring is going to be faster. Actually, using my calculator would be faster, but we'll do this. What multiplies to get -8? That adds to get +2 would be +4 and -2. Again, set those equal to 0 and solve. That establishes those critical points. Again, number line, smaller number to the left, bigger number to the right. Negatives are obviously smaller than positives. And again, now we've got less than equal to, so we're going to do solid dots. Whenever we do our interval notation, we'll be using brackets. And we just got to test to see if we end up with positive or negative values. And again, I'm going to plug it into this one because that's the one that's relating to 0. If I plug it in here, I've got to see how it relates to x minus 8. So that's kind of an issue. So we're going to plug it into this function in relation to 0. So again, pick a number smaller than -4. Pick a number between -4 and 2. Pick a number bigger than 2. Doesn't matter what you pick. Just make sure they fall within those ranges. okay? And to save a little time, it ends up working like so.
And always on that number scale, you're always.
Not necessarily, you're always looking for positives or negatives, because actually in this particular case, if it's less than 0, what kind of numbers are less than 0? Negative. Okay, the negative ones are the ones that are less than 0, so those are going to be my good solutions.
So the sign.
The sign matters. So when it's less than 0, okay, that's when we want the negative solution. So in this case, we want everything between -4 and +2. And again, we use brackets because this was greater than or equal to or less than or equal to. Had the line underneath it. The previous problem did not have the line underneath it, so that's why we were using parentheses. And infinity always uses parentheses. But in this case, we're not dealing with infinity. We're just saying between -4 and 2. All right, most of the problems are going to give you are going to be quadratic. Occasionally, though, they're going to throw in something different, like so. X to the 4th minus 9x squared is greater than or equal to 0. Now, this is a polynomial function. So again, your critical points are going to occur when the function is going to equal 0. You can use your calculator depending on the calculator you have, or we're going to do this one by factoring. In this case, these both have a greatest common factor. Everything is divisible by x squared. So if I divide that x squared out, x to the 4th divided by x squared is x squared, 9x squared divided by x squared is my 9. That's where this kind of came from. Okay, basically, remember, factoring out a greatest common factor is undistributing. So then if we set these equal to 0, then we solve, okay, square root it, x is going to equal 0. X squared minus 9, add the 9 to both sides. Again, square root it, x could equal plus or minus 3. So my critical points are 0, +3, and -3. Again, you have to read from small to big. So it'd have to go -3, 0, +3. So again, that plus or minus represents both +3 and -3. So remember, whenever you square root something, you have to account for both the plus and the minus. I didn't do it here because there is no such thing as -0. So this is just 0. But this one, when you square root it to get the x by itself, you have to worry about both the positive and the negative. Okay, anyway, this is a greater than or equal to. So again, we're going to use closed dots. We're going to use brackets. And now we have more regions to test. You're going to test something smaller than -3. You're going to plug it in, like -4 or -5. You're going to pick something between 0 and -3 to plug it in for this region, like -1 or -2. You're going to plug in something between 0 and 3, like 1 or 2. Check that region, then you'll plug in something bigger than 3 to test that region. And again, plug it into your original function, just plug it in for x and see if you generate a positive or a negative value. In this case, it plays like so. Okay, and remember, we're looking for the values that are bigger or equal to 0. So in that case, that'll be your positive values. Your positive values are going to be the ones that are bigger than 0. So all of these and all of these. Whoops. We're going to go from negative infinity to negative 3. And then we're going to want to go from positive 3 to infinity. Remember, infinity always gets parentheses regardless, so the greater than or equal to in the brackets only works for the numbers. Infinity always gets parentheses. And that's basically that whole lesson that covers your rational and polynomial inequalities. I'm going to throw one more example in there just because I don't like that my math lab does this, but it throws one problem right there at the very beginning that's not an actual inequality. The very first problem says what values make this equal 0. It's the same concept, so you're still going to factor or quadratic formula or however you want to solve. The only difference is if it actually equals 0, so if it is not an inequality, when you write your solutions, they just do it as a set of numbers. So it's going to look like this. And it's just a goofy thing that they throw in my math lab to get you. Okay, again, that's not something I'm going to do on the test or anything like that. I'm not trying to get you. Okay, 4-6 is all about inequalities. I would not throw a problem with an equality, equal, in there. But if they do, just understand that you're writing your solutions as a set, not as an interval. So everything we did with inequalities, on focus, okay, we ended up writing as an interval. Okay, inequalities gives you an interval. Okay, inequalities gave us an interval. And equality, okay, these are actual zeros. These are values that make it equal 0. We don't have to worry about the plus and minus. We don't have to worry about shading anything. Okay, we're trying to figure out what actual numbers make it equal 0. And it would be just these two. So they do throw one tricky one in there just for no reason. I'm not sure why they did that, but just because. But then most of it is doing those inequalities where you're going to be shading. So remember, test next time. Again, Republic people, I'm assuming I'll hear back from the Proctor Center, and I'm assuming they'll play it just like they did last time. If that's not the case, I will let you know as soon as I know. Get this on me. Okay. So again, Lebanon people, we're testing here in class seated. You need to be here. Like I said, Republic people, hopefully you'll test in your classroom during class time with a proctor. Waynesville people, you will need to set up a proctoring time. So at some point or another, you're going to need to contact that proctoring center. And I think the hours were Tuesday for Tuesday through Thursday from 9 a.m. to 2 p.m. and then Friday from 9 a.m. to 1 p.m. So test next week. That's all we got. No new lessons, and then spring break after that. Make sure you're getting your homework done. Practice the My Math Lab stuff. That's going to be the stuff that's going to prepare you for the test. Be ready to go. That's all I got. See you guys. Also, if you get stuck on anything, you need to email me. Do so.